Hello everyone, this is your Captain Malleo speaking. Today's flight path has been generated and optimized by a genetic algorithm to ensure fastest travel to your destination.
Before we get to the focus of this video, I first want to mention that the 100% tool-assisted speedrun for Paper Mario: The Thousand-Year Door is almost underway. I've just wrapped up a walkthrough of the route to test that everything works as intended, and at the time of this video's upload, there's a good chance I've already started working on the task itself. If you're interested, you can watch me livestream my work on the tasks over at twitch.tv/taskmalleo. Each time I start one of these tasks, I always try to learn or implement something new to make sure a new task for TTYD stands out amongst its predecessors. With this in mind, I had to think of something that I always struggled to optimize in-game. And immediately I knew what our focus should be this time: plane flights. Near the end of the prologue, a black chest grants you the ability to turn into a paper airplane, and this ability can be used to traverse long gaps that would not be traversable otherwise. While flying the plane, you can nosedive to gain speed but lose height, or pull back to gain height but lose speed. The objective is simple: take off and land on the other side of the gap as fast as possible. And given that plane flights are pretty simplistic, they're easy to optimize for tool-assisted speedruns, right? To say that plane flights are simple is wrong for a multitude of reasons. There's an unnatural speed cap, which means we can't model flights after real-life physics. There are 145 unique controller inputs that will result in different plane flight angles, and the various distances between the takeoff and landing platforms across the game means that the general path that we have to fly in changes on a case-by-case basis. There are just too many variables to reliably determine what would be considered an optimal flight path. But what if I told you that every plane flight you're seeing on screen is optimal? What if I told you that every flight you're seeing on screen is not done by a human in any way, shape, or form? With the immense help of Trebuchet, the inputs generated to complete these flights were created entirely by a program that simulates the in-game flight physics and trains itself to find the fastest flight possible using a genetic algorithm. This video will show examples of what were assumed to be optimal flights from experienced speedrunners as well as the current any percent tasks, and compare these perspectives to flight paths computed by the program. We will also show the process behind reverse engineering the plane flight physics and explain what exactly a genetic algorithm is and how it actually functions at both a simplified and a technical level. Putting an end to years of uncertainty, this is how we trained a genetic algorithm to fly optimally in Paper Mario: The Thousand-Year Door. Buckle up and please prepare for takeoff. To start explaining how we got this project working, I first want to talk about the process of reverse engineering the game's flight physics. If we want a program to fly, then we first need to accurately simulate flights that can occur in-game. So, we need to mimic the in-game flight physics. In order to precisely match the computations that occur when flying in-game, I made use of Ghidra, which is a declassified NSA tool that transforms the game's assembly code into C language code, which is much easier to read. From there, I essentially had to copy over this generated code, tweak it a bit, and get it to compile and run on its own. The end result is a function which, given the current state of the plane flight and a GameCube controller analog stick input, outputs the next frame's position, speed, and other important variables. This new data can be used to compute the next frame, and the next, and so on. To attempt to clean things up a bit, I tried to compartmentalize some of the code, which branches into very large sections depending on whether you're nosediving or tail diving, or whether you're holding neutral or not. It's not the cleanest code, but it'll do. Let's skim through some of the code that I scrounged up. Here's a function the game uses to restrict an angle to between 0 and 360 degrees. Here's a function the game uses to compute the sine and cosine of a number at the same time. This function will run if we're not touching the GameCube controller analog stick. If we're nosediving, and if we're also above the plane panel, then it bumps up our speed. Otherwise, it does some other stuff related to plane rotation based on how close to the speed cap you are. If we're pointing the analog stick left or right, then this code runs. and based on how far left or right we're pointing the stick, and based on what direction we're flying in, it adjusts our rotation. If we're nosediving, then this function updates our speed based on our new rotation. Then, depending on the state of the flight, it can do some other stuff to adjust our rotation further. Otherwise, if we're tail diving, then this function does some other things to adjust our speed and rotation. Here's a compartmentalized section of code relating to our position coordinates being updated. And here's the high-level function that calls all the previous functions I mentioned. Given an analog stick position and the current state of the flight, it'll somehow end up spitting out the correct state for the next frame. Separate from that, we also need to tell the program what our starting conditions are. Where are we starting the flight from? Which direction are we flying in? Where do we want to land? For the first 2 points, we can make use of a Python class created by JD Aster to read important variables from a copy of the game's RAM, which we can export at the start of the flight. We then manually specify the landing platform boundaries, which will vary for the different plane flights. This data is then fed into our main function, which uses it to initialize the flight. With the physics simulation and initial conditions handled properly, we now need a way to actually generate a sequence of inputs which, following the rules set forth by the physics simulation, actually manage to take the player to the landing platform, and do so taking as few frames as possible. This is where Trebuchet comes in, and he'll take over to explain what exactly a genetic algorithm is, and how we were able to make use of it for this scenario.
I'm Trebuchet, and I'll be discussing the gory details of how a genetic algorithm, or GA, works. A GA is a type of optimization algorithm that's inspired by evolution. Let's tackle these terms in turn. We'll start with the idea of an optimization algorithm. The basic idea is that we have some complicated process. This process has lots of settings, and we want to know which configuration of settings does best. For example, a company might want to know what prices to charge for its various products in order to maximize profit. Or in some industrial process, you might need to determine the optimal flow rates of components in a chemical reactor in order to maximize the yield. In our example, we have a video game that simulates flying a paper airplane, and we need to choose controller inputs in order to make the flight as fast as possible. It's generally not reasonable to try to optimize the configuration of settings in the real world. For example, you wouldn't want to just randomly try increasing the flow rate of an expensive chemical in a reactor, nor would you randomly double the price of one of your products to see if you make more money. For the plane game, it takes several seconds to run a flight in an emulator, and we may try several million flights as we search for the best one. So instead, we construct a mathematical model of the process that allows us to quickly try out lots of possible configurations. An economist might build a model of sales in order to identify the optimal prices for a company's products. A chemical engineer might build a model of the chemical reactions inside a reactor, and Malleo has figured out how the game's physics model works, and he produced a program that runs the same physics, but way faster. All optimization problems have a similar theme. We have some number of settings, be that prices for each product, flow rates of each chemical, or controller inputs on each frame. We also need a measure of how good a particular configuration of settings is, be that by measuring profit, chemical yield, or in our case, flight duration. There are many ways we could approach an optimization problem. As a first pass, we could just try a million random configurations and choose the one that gives the best fitness. We could try tweaking each of the settings to look for improvements, or we could call in an expert and ask for their opinion, and so on. Now that we know what an optimization problem is, we can discuss how a genetic algorithm can be used to tackle an optimization problem. A genetic algorithm is an optimization algorithm based on Darwinian evolution. So let's talk about evolution for a moment. In Darwinian evolution, organisms that produce many children will survive, and organisms that produce few children will die out, all other things being equal. We say that organisms with more children are more fit, or that they have a higher fitness. Consider a petri dish with some organisms in it. Each organism has a sequence of DNA. For the moment, let's assume they all start with random DNA sequences. Biology had to start somewhere, after all. Some of these DNA sequences will increase an organism's fitness, allowing the organism to produce more children. But the children won't be identical copies of their parents. Two things can happen: mutation and mixing. In the case of mutation, a parent organism attempts to copy its DNA to its child, but some of the DNA bases are copied incorrectly. Many times this will be harmful to the child, but occasionally a beneficial mutation will be introduced. But a more interesting case is mixing, where two organisms mix their DNA to produce children that have aspects of both parents. A simple mixing scheme would be that a child has the first half of its DNA from dad and the second half of its DNA from mom. This means that if one organism has a bit of DNA that's good for one thing, and another organism has a bit of DNA that's good for something else, they can combine to produce a child with high fitness. Or they could produce a child that has the bad parts from both parents, since mixing happens at random. So now we've done mutation and mixing, and produced a lot of candidate children. Some of these children will have low fitness due to unhelpful mutations and ineffective mixing, so they will die out. Other children, however, will be even more fit than their parents. These are the organisms that will survive to the next round of producing children. In GA terminology, we call one round of this process a single generation. This process repeats over and over again until the resulting organisms are as fit as they can be. This explanation leaves out lots of important biology, but it encompasses all the basic concepts we need to understand how a genetic algorithm works. A genetic algorithm is analogous to the Petri dish example, except that instead of DNA, an organism is defined by a configuration of settings for some process, prices, chemical flow rates, or controller inputs, and the fitness is determined by our model of the underlying process. In this way, good configurations of settings will gradually displace bad ones, and beneficial mutations and mixing events will be retained. We're almost ready to watch the GA optimize a flight, but first I need to explain how we measure a particular flight's fitness. Obviously, if the plane just careens off to nowhere, that flight is bad, and a flight that makes it to the target slowly is not as good as a flight that makes it to the target quickly. So a naive fitness function might look like this. So here, if a flight doesn't land, we give it a score of 0, and if a flight does land, we give it a high score, but then subtract out how long it took to land, so that a flight that arrives at its target more quickly gets a higher fitness. But there's a problem. At the beginning of the optimization, it's likely that none of the flights will land. For example, here are 2 flights, neither of which land. So how do we determine which ones we should use to build the next generation? They both have the same fitness. The solution is to say that the flight that got closer to the platform is more fit. A more subtle problem occurs in the case where we do land. Let's say we have 2 flights that last 64 frames. Both of these flights will have the same fitness, but we'd rather keep the flight that was closer to getting 63 frames. So we modify the fitness function a bit. In this new version, if you didn't land, your score is not 0, but rather based on how close you got to the target. If you do land, then you're penalized for how long it took, as before, but you're now rewarded based on how much you overshot the target. This way, if we have 2 flights that didn't land, we'll keep the one that made it closest to the target, and if we have 2 flights that landed, we'll keep the one that got further past the target. If we keep getting further past the target in the same time, eventually we'll make it to the beginning of the target 1 frame earlier. So, how do we make mutations and do mixing for our flights? Remember, the DNA in this case is the controller inputs on each frame. We have a couple options for how to make mutations. Option 1 would be to pick a random controller input, a random frame, and change it to another random value. Option 2 would be to pick a random region and set all of the inputs in that region to a random value. Option 3 would be to again pick a random region, but now increase or decrease all of the controller inputs in it by a small random value. Option 4 is to pick a few random input frames and either delete them or duplicate them at random, sliding the other input frames to compensate. There are a few other variations we use for mutation, but this captures the basic ideas. Now, how do we mix? This is the most complex part of the algorithm, and it also turns out to be the most important. We start with 2 parents. Let's call them mom and dad. First, choose a random block of inputs in mom and another random block of inputs in dad. Note that these blocks will not likely be the same size. Take the block from mom and squoosh or stretch it to be the same size as dad's block. This squooshing/stretching operation is sort of complicated, so let's take a look at the block of mom's inputs that we'll be stretching. The block of inputs we selected from mom contained 15 frames, and the inputs are shown here as red dots. Now the block we selected in dad is 20 frames long, so we need to stretch mom's inputs to match. That's simple enough. But now the inputs don't line up with the frame boundaries, and of course we need a value for the controller input on every frame when we put these data into Dad's block. We generate the new inputs by first drawing lines between all the points in our stretched inputs from Mom. And now we find out where those lines intersect the frame boundaries, shown here in blue. So now we have a set of controller inputs that follows the contour of Mom's input, but that fits in the block we took out from Dad. We do the same with Dad's block of inputs, stretching or squooshing it to fit in Mom's block. Okay, going back to our real example, here's the result of crossing those two parents. One more thing, before we can watch the algorithm do its magic. At the end of each generation, we delete all of the parents except for the single best one. That way we don't delete our best flight, but we don't allow the population to become stagnant with many copies of nearly identical inputs. The parents in the next generation will thus be the single best parent from the last generation, and all of the best children from the current generation. Alright, let's take a look at how the algorithm tackles the flight to get to blooper. To keep things manageable, I'll use just 5 parents for every generation. We start out with 5 completely random input sequences. We have no idea how good these flights will be, so we need to measure their fitness by simulating them. Just for fun, let's watch what happens if you use the pink inputs to attempt this flight. Well, that was disappointing. Here are the results from all of those flights, starting on the left and attempting to make it to the platform shown on the right. While these initial flights are almost comically bad, they contain the seeds that will be used to generate all of the future flights. So now, we let the algorithm generate the first generation of children by mixing and mutating those initial parents. Here we can see the set of candidate children generated by the algorithm in this first pass. I should point out that all of the initial parents are in this collection. After all, if none of the children improve on the parents, we should make sure we keep the best parent around. Okay, let's simulate all of those children. Well, that's bad, but encouraging. Already we can see that some of those flights got much higher up the wall. We now remove all but the 5 best flights from this generation in order to have the next generation have a better set of parents. Here are our 5 best flights. So now we pass these back through the mutation and mixing process and get a new pool of possible children. We can already see that one of these flights is getting pretty close to the goal. We select the 5 best flights again, shown here, and now lather, rinse, repeat. Here are the children from this generation. And the 5 best flights. We mutate and mix those flights and generate more candidate children. Well, looky there. After just 4 generations, the genetic algorithm has already managed to land the flight. I ran this algorithm for 10 generations, so let's quickly watch the progress over the next 6 generations. And from just that very quick optimization process, we've generated a flight that doesn't look half bad. Here it is in game.
Now that you all know how our program works, let's see how it performs against humans and the task when applicable. Let's first focus on the plane flight right before the blooper room in Ropeport Sewers. This is a pretty short flight, but the algorithm can still manage to shave off a good number of frames. To give you a couple perspectives, we'll show 3 different plane flights. The first is what an RTA runner's plane flight may look like. The next perspective is the plane flight used in my most recent any% task for TTYD. Lastly, this is what the genetic algorithm generated. Monato's flight looks pretty good, but comes about 20 frames short of what the algorithm was able to achieve. This may not sound like much, but a better way to look at it is that the algorithm was able to reduce his flight duration by about 30%. For the TAS's flight, it looks pretty optimal, but it's still a handful of frames slower than what the GA was able to achieve. For a task where every frame matters, time saves like these can be immensely important, especially knowing that the time save will add up since we fly several times throughout the game. On screen are some more plane flight comparisons between RTA runners and the algorithm. One area I'd like to touch on is how genetic algorithms tend to break things. There's a great video by 2 Minute Papers which talks about the use of OpenAI for a video game simulation with 2 seekers and 2 hiders. At some point, both teams end up discovering bugs in the physics engine that can be exploited to gain a significant advantage over the opponent. When you're in flight above a plane panel, you can repeatedly move the analog stick from neutral to either left or right depending on which direction you're flying in. And as a result, you'll actually maintain forward speed, but the tilt of the plane will cause you to build significant amounts of height. Similar to the OpenAI example earlier, our algorithm actually wandered upon this bug when we specified that we wanted to focus on gaining as much height as possible. So if the genetic algorithm finding a bug on its own isn't cool, I don't know what is. We long wondered if you could take the plane panel in the room before Grotus's lair and land up top by Gloomtail's room. Doing so would offer a faster method to perform a glitch we just called a Gloomtail warp. Using the aforementioned glitch along with the genetic algorithm, we can gain a good amount of height before even worrying about the plane flight itself. After running through several 100,000 generations with the genetic algorithm, we sadly came just under 100 units short. But thanks to the genetic algorithm, we know it's pretty safe to say that we cannot reach Gloomtail's room via the plane panel. In closing, tassing isn't always just about slowing the game down. In previous videos, I've touched on the importance of using RNG manipulation or calculus optimization problems or crowdsourced tree traversals to shave off significant amounts of time from an otherwise considered perfect speedrun. These methods are an important consideration for achieving and verifying that something is optimal. Some may question why exactly this was necessary. I mean, we're just playing video games after all. Well, if you've watched the video up until this point, then that means the premise of using genetic algorithms in a video game to optimize a speedrun tricked you into learning about how they work. Previously, I had very minimal understanding of how genetic algorithms worked, yet Trebuchet's expertise has given me the opportunity to learn about genetic algorithm principles through something I'm already familiar with, optimizing TASes. Sure, this may not be the most serious application of something so complex, but in the end, I learned something and I hope you did too. And that about wraps it up. Actually, just kidding. I couldn't forget about the plane minigame, come on. Let's see how well the algorithm does while I wrap up the video. Thank you immensely to all the RTA runners on screen for recording some flight footage we could use to compare against the program. Be sure to check out Trebuchet through the links on screen. Again, I can't overstate how helpful he was on getting the ball rolling on this project and handling the genetic algorithm side of things. Lastly, be sure to tune in to the live development of the 100% task for TTYD over at twitch.tv/taskmalleo. Thank you for flying with us today, and have a good rest of your day.